We've got two magnets here, and we're discovering, not surprisingly, that opposite poles attract. The red pole is north, and the unmarked pole is south. According to Faraday, when a conductor is pulled across magnetic field lines, an electric current flows in the conductor. Now, we already know that a current in a conductor will in turn create another magnetic field. And the important point, and this is a really, really critical point, and it's why Lenz's law is so important, the magnetism that's created in the ring fights the change in magnetism that produced it. So in other words, when I try to push this magnet through the ring creates a magnetism that pushes back. So I don't get something for nothing. I don't get an electric current without working. Let's set up a demonstration. We'll take the aluminum ring we started with. It's light and it's not magnetic. We'll drop the ring between the poles of a very strong horseshoe magnet. If there were no magnetism here, the ring would fall under the influence of gravity. But as it enters the poles, we induce a current in the ring because we're increasing the number of magnetic field lines, or what we call magnetic flux, enclosed within the ring. A current starts flowing in the ring becomes an electromagnet. The poles of the induced electromagnet oppose the poles of the horseshoe magnet, and so the magnetic field of the big magnet creates a net upward force on the ring, opposing the force of gravity and slowing the ring's descent. As the ring exits the pole region, the flux that it encloses starts to decrease, inducing a current in the opposite direction. But that current also opposes its fall. In each case, the ring falls much slower than we expect it to. This is because Lenz's law applies. One of the critical tests of a scientific theory is whether we can predict anything. If what we've just said about Lenz's law is true, if we can keep current from flowing in the ring, the effect disappears. So what if we were to take the ring that we just dropped and put a small cut in it so there was not a closed path for current? According to that, the ring should not be influenced by Lenz's law, and it should drop entirely under the influence of gravity. Here we've got a ring with that cut in it. When we drop it through the magnet, we note that it falls unimpeded with no surprising delays, as we just saw in the previous example. Another way to have a look at Lenz's law would be to imagine that instead of one ring, as we've just seen, we had many rings, and those rings were stacked together to form a tube. If a magnet were to go down that tube, it would induce a current in each ring, and each current would fight back against the magnet. So we'll take a thin tube and a powerful magnet. The tube, of course, would be not made out of iron or steel, so that there were not any magnetic effects on the tube. Let's drop a pencil through the tube, a non-magnetic object, to see that under normal circumstances, gravity controls the behavior, and the pencil falls through as rapidly as we expect. But when we drop a magnet through it, it takes much longer. Why is that? As the magnet falls through the tube, the obvious force acting on it is gravity. But along with gravity, as it falls through each ring of the tube, it induces a current around the ring. The current produces a magnetic field that pushes back on the magnet. So the magnet's now feeling three forces: one downward from gravity, one upward as the lower electromagnet repels it, and one upward as the upper electromagnet attracts it. The two magnetic forces counteract the gravity, and so the magnet falls at a constant velocity instead of accelerating like a freely falling body. So why does Lenz's law matter? Well, it matters because it tells us we can't get something for nothing. That when we make electricity, we make it by fighting magnetic fields, by pushing, so that we still need mechanical energy to make electrical energy. Energy is conserved even if we switch forms from mechanical to electrical. We can see Lenz's law come into play in many places. One of the more interesting places is in the behavior we call maglev, or magnetic levitation. Magnetic levitation generally applies to an object moving over a long distance of a non-magnetic conducting material. We can't set up a long track like that fits in our laboratory, but if we take a stationary magnet and a spinning aluminum disc, we can get the same effect. We have a spinning aluminum disc underneath a strong rare earth button magnet. As the disc spins, we'll hear the noise of the magnet scraping along the aluminum disc. And as the aluminum disc picks up speed, the rate at which the magnetism changes for each surface area point of the aluminum gets higher and higher. That induces more current, and more current produces more magnetism. If we move fast enough, the induced magnetism pushes back on the button magnet with its own weight, and it lifts the magnet off the surface of the aluminum. We've now seen 3 demonstrations of Lenz's law. In all of them, we have discovered that if we produce electric energy, we've got to do so by putting in mechanical energy. That the laws of physics that we've learned in mechanics transfer right over to electricity and magnetism. That forces come in pairs, that energy is conserved, and that these electrical behaviors that are not as intuitive as the mechanical behaviors still follow all the rules. We don't get something for nothing in electricity any more than we did in mechanics.